Good morning, everyone. My name is Hugh, and it was such a big honor for me to be here today to present to you about our work, which is the sports visual data analysis with deep vision. So first of all, in my presentation today, we will go through this five sections, including the introduction, related words, proposed method, software development, and the conclusion and future work. So firstly, you might see here there are 4 different events in a soccer match. So the question is how we can determine which action is presenting in each event. Do we need some people to manually assign them one by one, or do we just need to use some algorithm in deep vision to do such a task? So this is the motivation for us to conduct research on action spotting. So what is action spotting? To determine the definition of action spotting, you might know that it is both hard and ambiguous to define when an action begins and ends in soccer. For example, it not only clears when a certain action, such as creating a ball or scoring a goal, happens. So in the scope of our work, we redefine action spotting by to indicate the timestamp when an action happens and by the associated events of that action. Our objective is to create a data annotation and visualization platform integrated with a soccer action spotting model. So our first object is to create a model that can predict actions such as kick off, goal, ball out, play, red card, yellow card, and so on in a soccer match. Secondly, we want to design a scalable analysis and visualization platform. Our main result, we propose based on the previous working experience with audio classification. We propose a temporal multimodal architecture that utilizes both visual and audio features. We evaluate this model on SoccerNet version 2 dataset, which improved the accuracy from 53% to 57% in MAB scale. And our model can predict 17 types of events in soccer, such as goal, shot on target, red card, and you name it. And also we designed and implemented an annotation and visualization platform adopting our proposed method and algorithms. Let's take a look at the related work. We found out the SoccerNet version 2 dataset, which is the largest public annotated dataset. It includes more than 500 video in soccer and more than 300,000 temporal annotation. This annotation is divided into 17 groups, such as penalty, card event, offside, direct free kick, etc. There are many research proposed their method on the task of action spotting in soccer. Audio bit is proposed by Van der Plate. It is an approach for detect the action in soccer video using multimodal fusion architecture that employ both visual and audio features. However, this model has achieved an accuracy of 73% in the first version of SoccerNet, which has only 3 classes. When it comes to a larger dataset which has 17 types of classes, the accuracy drops significantly to nearly 40%. Another work on action spotting is proposed by Cha and Kola. They propose 2 Boolean techniques called NetVLab and NetVLab++. Their method achieve an accuracy of 31% and 53% respectively. So let's come to our proposed method. based on the two formers method that I have mentioned earlier, we propose a multimodal architecture that employ both visual and audio feature and using the NetVLab++ pooling layer. So firstly, for the visual submodule, we use ResNet 152 for feature extractor. After extract the feature, we feed it into the NetVLab++ pooling layer. So what is NetVLab++ pooling layer? It is a temporal aware pooling layer improved from NetVLab, which is the generalized VLab layer. Stand for vector of locally aggregated descriptor. Please look at the function of original VLab. We must see that this function is discontinuous, so it cannot be used in CNN model. So NetVLab solved this problem by propose a soft assignment run from 0 to 1 to make it differentiable. After doing calculation, this is the final formula for NetVLab. But if we use NetVLab alone, it will confuse between the past temporal context and the future temporal context. So the NetVLab++ is an improvement of NetVLab, which use two separate NetVLab layer for the past context and future context. As for the audio submodule, we use VGGS for feature extractor. Then we feed it into the NetVLab pooling layer, similar to the visual features. We demonstrate a audio of a match here. Each event is denoted by the red asterisk over there. So as we might see that whenever an event happens, the audio reach a peak in audio. So we think that the sound and events have some connection together. So we concatenate the visual feature and audio feature. Then we drop out the probability larger than 40%. Come to a fully connected layer and end it with a sigmoid function. So this is the result of our method. We have improved the accuracy more than 16% over audio bit and 3% more than NetVLab original. In a higher detail, there are three classes that have a significant improvement. This is Go, which improved more than 11%, red card 8%, and short on target 9%. But on the other hand, there are two classes that have slightly decreased the accuracy of over 5% and 0.3%. This is the really small number. You might notice that those events that have a significant improvement, that they will have gained a lot of attention from the audience, such as when a goal happens, there will be shout out from the audience in the stadium. When a red card happens, there will be a whistle from referee. As for the events that decrease the accuracy, which have less attention from audience, which is the proven that the audio has a positive infection on the overall accuracy. So let's come. We have developed a small AI annotation platform integrated with our proposed method. Well, in conclusion, we have adapted the temporally aware cumulative technique into the action spotting task. Secondly, we propose a multimodal architecture that utilizes both visual and audio features. Thirdly, we evaluate the proposed method on StockNet version 2 dataset and improve the accuracy and improve the results more than 3% as compared to the original baseline model. The goal and shot on target event have gained a significant improvement. And also we developed a sport annotation and visualization platform on web environment. This platform is adopted our proposed method and algorithms and deployed at the UIO. For the future work, we want to conduct further research on the relative poor accuracy to improve that. There are some classes that have less data than other classes, such as red card, penalty, and goal. So we might want to augment the data on those classes and support a wider variety of sports. And that's my presentation. Thank you for listening.
Thank you. Very interesting application, especially this players. It's a FIFA World Cup. And we have time for a couple of questions, please. Yes.
Yeah, I would like to specify the audio input of your model. Is the original sound in the stadium or the commentary?
This is the original sound, which has the audience sound as well as the referee sound and the commentator also.
Does it contain the commentary?
Yes.
Other questions? Yeah, please.
Thank you very much. Very interesting. So I'm very much interested in the performance improvement for red card.
Yeah.
And you mentioned about the whistle,
Yeah.
right? But you compared the performance with the audio bit baseline.
Yeah.
And audio bit uses audio, but the performance is not so high.
Yeah.
Can you explain why this happens?
Well, this is the improvement because we use the NetVLS layers that separate the context before and after an action happened. So when a red card is show up, there will be a whistle before. So by separating the context into parts will help will improve the accuracy.
I see, because of the temporal.
Yeah.
I see, very interesting. Thank you.
Thank you. Other questions?
May I have one question? In fact, you combine visual and audio informations.
Yeah.
But I really not quite sure how do you process frame by frame and the audio, how do you sample it? And finally, do you do the classifications or just binary classifications? Can you specify it?
But, so there are two questions. So firstly, how do we process the audio features? Because the visual feature will be extracted at the frame rate 2 seconds to FPS, right? So for the audio, we use for every half a second we extract audio one time. So the audio dimension will exactly to the visual features. And for the second question, that is, sorry, can you?
Do you do the binary classifications or the
Or multi-class?
normal?
Yeah. This is the multi-class classification problem because we classify we classify each window chunks. So in a window chunk, there can be several actions that happen. Like in 5 seconds, there can be a corner play and throwing at the same time. So we use the multi-class classification problem.
But one even may long event, or because here you just take a window, right?
Yeah.
1 second, and you do the classifications. But one event may long or may short. So I would like to know how do you determine the beginning and the ending of one event.
The action spotting is our action spotting is to indicate the timestamp when action happened, not indicate the begin and ends of the action. So we just define a single timestamp only.
Okay, so this means you give only decision for one window. Yeah. Okay. Other questions? Yes.
Did you try other strategies to fill the audio and the visual stream
Yeah.
besides concatenation?
I haven't tried it yet, but it's a very good idea. So I will take it into the consideration in future work.
Okay, thank you.
Thank you.
Okay. So let's thank our speaker then. So I don't have the program, so I have to look. So the second presentation, I put the paper entitled "A Study on Skeleton-Based Action Recognition and its Application to Physical Exercise Recognition." Please.
So, good morning everyone. My name is Pak Rotin. I'm just graduated from Harvard University of Science and Technology. So today I'm here to talk about you about our work in last several months. So our topic is a study on skeleton-based action recognition and its application on application to physical exercise recognition. So my presentation is split into a 6-part introduction, related work, the physical exercise data set construction, the proposed method, experience, results, and conclusion. So first, let's jump to the introduction. Our idea was from last year, while the COVID-19 is still a huge problem for our world. So people have to stay at home all the time, and to keep them healthy and fit, they have to physical exercise by themselves, following the instruction from the TV shows on the internet, and that practice without supervisor can cause risk to their health. So therefore, the physical moral application with self-assessing physical exercises become more and more popular. So about the physical exercise assessment, there are 3 main parts. That are the manual instruction, when the code has to be with you all the time, like 24/7. You can use the wearable devices to